Hello viewers, in today's session we are going to discuss a very important integral in which we are going to discuss the application of beta and gamma functions, right? So here we have to evaluate this integral which is 0 to infinity, and we have x square over 1 plus x raised to 4, right? So let us start. So let us first take this integral as I, right? Now here what we will do, we'll first take help of the method of substitution, and we'll take the term x raised to 4 as t, right? So here our new variable is t, and we are making this substitution because we are going to convert this integral into the beta function. So now we have x raised to 4 is equal to t, so that x can be written as t raised to 1 over 4. Now let us differentiate x with respect to t. So we have dx over dt is equal to the derivative of t raised to 1 by 4, and here we'll make use of the power rule. So we have 1 over 4 t raised to 1 over 4 minus 1. So this is 1 over 4 t raised to minus 3 over 4, right? So now dx can be written as 1 over 4 t raised to minus 3 by 4, and here we have dt. So the value of dx is given by this expression. Now see, here the limits of integration vary from 0 to infinity. So let us change the limits accordingly. So when x is 0, then the value of t is also equal to 0, right? And when the upper limit, that is x, tends to infinity, then t also tends to infinity. So the limits of integration remains the same. So we can now write this integral I in terms of t as 0 to infinity. Here we have x square. So x square can be written as, because x is t raised to 1 by 4, so we can write t raised to 1 by 4, and here we have square, and in the denominator we have 1 plus t, because x raised to 4 is t, and then we have dx, and dx can be replaced by 1 by 4, t raised to minus 3 by 4, and here we have dt. So now let us rearrange the terms. We can take 1 by 4 outside the integral. We have 0 to infinity. Then we have here t raised to 2 by 4, and here we have t raised to minus 3 by 4. So the bases are same, so we can add the exponents. So here we have minus 3 by 4, and in the denominator we have 1 plus t, right? Okay, so now we can write it as 1 by 4, 0 to infinity, and here 2 minus 3 is minus 1, so we have t raised to minus 1 by 4, and here we have 1 plus t, right? And this is dt. So now let us change this integral into the beta function, right? So for this we'll make use of the definition of beta function. So beta function is given by beta m comma n, and here we have the integral 0 to infinity, and we have t raised to say m minus 1, and here we have 1 plus t raised to m plus n, and here we have dt. So this is one important form of beta function. So beta m comma n is given by this integral. So now here we have the terms which are similar to this integrand. So here we have t raised to minus 1 by 4. So now we can take m minus 1 as minus 1 over 4, right? So if we compare these two integrals, we can now write m minus 1 is equal to minus 1 over 4, and here we have 1 plus t raised to 1. So this m plus n may be written as equal to 1. So now we have two equations and we can find out the values of m and n. So m is given by minus 1 by 4 plus 1. This is 3 by 4, and the value of n can be obtained by taking m to the right hand side. We have 1 minus m, that is 1 minus 3 by 4. So this is 4 minus 3, that is 1 over 4, right? So now substituting the values of m and n, we can now write this integral I as 1 over 4, and we have 0 to infinity t raised to minus 1 over 4. Now minus 1 over 4 can be written as m minus 1. So m is 3 by 4. So we have 3 by 4 minus 1, and here we have 1 plus t raised to 1, right? And 1 can be written as m plus n. M is 3 by 4 and n is 1 over 4, and here we have dt. So now this integral is our beta function. So we have I is equal to 1 by 4 times beta of m comma n. M is 3 by 4 and n is 1 by 4. So now we have to find the value of this beta function by changing it into gamma function. So now we know the relationship between the beta function and gamma function, that is beta m comma n is given by gamma of m gamma of n divided by gamma of m plus n, right? So now the integral I can be written as 1 by 4, and we have gamma of 3 by 4, then gamma of 1 by 4, and here we have gamma of 3 by 4 plus 1 by 4, right? Now this term is equal to a gamma of 3 plus 1 4, 4 over 4, that is gamma of 1. 4 and 4 get cancelled and gamma of 1 is equal to 1, right? So now we have I is equal to 1 by 4 times gamma of 3 by 4, and here we have gamma of 1 over 4, right? Now we have to calculate the value of this term, and to calculate the value of this term, we'll make use of the famous Euler's reflection formula. Now the Euler's reflection formula says that gamma of 1 minus n times gamma of n is equal to pi divided by sine n pi, right? So now we can express this term as gamma of 1 minus 1 by 4, because 3 by 4 can be written as 1 minus 1 over 4, and here we have gamma of 1 by 4. So now this term is similar to this one, right? So here we have 1 minus 1 by 4, here we have 1 minus n, and here we have gamma of n, here we have gamma of 1 by 4. So comparing this term with this one, we can see that the value of n is 1 by 4, right? So n is 1 over 4. So now the value of this integral I can be written as 1 by 4, and this expression can be replaced by pi over sine of n pi. N is 1 over 4, right? So we have sine pi over 4. So we have 1 over 4 pi and sine pi by 4 is given by 1 over square root of 2. So this is pi times square root of 2 over 4, right? So taking square root of 2 to the numerator, we have pi times square root of 2 over 4. Now we can rationalize this expression by multiplying the numerator and denominator by square root of 2. So we have pi root 2 over 4 times root 2 over root 2. So now we have root 2 times root 2 is 2. So this term is cancelled by this one, and here we have 2. So we have pi over 2 times square root of 2, right? So viewers, the value of this integral is equal to pi divided by 2 times square root of 2. So this is how, by making use of the concept of beta and gamma functions, we can evaluate these kind of integrals, right? And moreover, here we can also find out the values of these type of integrals by using the method of residues, that is Cauchy's residue formula.